Quadratic functions are one of our most important types of functions because they can be used to model what's called projectile motion. Now, we live in what's called a gravitational field. While you may not understand all the physics of that gravitational field, you have experiential knowledge of that gravitational field. So let's think about a really simple example. Let's suppose it's a beautiful day and you decide to take your dog to the park. You're going to go to the dog park and you're going to play fetch. So you have some kind of a ball and you're going to throw this ball for your dog. Now, based on your experience, you know that ball leaves your hand. It goes up into the air and it slows down. It eventually comes to one little instantaneous stop, and then gravity is going to cause that ball to accelerate back down to the earth. The exact path that that ball takes is a perfect parabola. So let's be more precise. When an object is launched, thrown, or shot into the air, the object is called a projectile. When a projectile is launched vertically into the air with an initial velocity of v0 meters per second, so when the ball leaves my hand, it's going to have a velocity, some initial velocity, and by the way, initial means at time 0. So we denote this by putting a subscript 0 on our velocity. So v0 or v sub 0 means initial velocity. Likewise, initial height can be denoted h0 or h sub 0. So if I know the initial velocity that that ball leaves my hand, and I know how high above the ground that that ball leaves my hand, the initial height, then we can predict where that ball is on any path of that parabola at any moment in time. And we can model this with the function h of t equals negative 4.9 t squared plus v naught t plus h naught. So again, you can see our initial velocity here on our linear term. You can see the initial height programmed in right here. And this term relates to gravity. Now, the exact constant that's used on this quadratic term depends on the units that I'm using. So if I'm looking at metric units, meters per second, the initial height is meters, then that leading coefficient is going to be negative 4.9. However, if the initial velocity is given in feet per second and the initial height in feet, then that changes that first coefficient to negative 16. But the other terms stay exactly the same. So be sensitive to which units that you're using. With this model in mind, let's look at an example. We'll do a little sports analysis here. At an Amarillo College baseball game at Hodgetown, a player swings and hits a pop fly straight up into the air to the catcher. The height of the baseball in meters t seconds after, let me put a little comment here, in meters, t seconds after the crack of the bat is given by the quadratic function h of t equals negative 4.9 t squared plus 34.3 t plus 1. So we already have our model. The first question, what was the initial velocity of the baseball? Now remember, in our model, initial velocity is programmed in as the coefficient of our linear term. In this case, we have 34.3. So we know our initial velocity v0 is equal to 34.3. But we also need to know what are the units on this initial velocity. Based on the nature of this coefficient, we can tell that we're using this model. And in this model, initial velocity is given in meters per second. So our baseball then leaves the bat at 34.3 meters per second. What was the initial height of the baseball? Now remember, from our model, initial height is this term right here. So in our case, the constant there is 1. So our initial height, h naught, is equal to 1, and we're using metric units here, so 1 meter. Question C, how long does it take for the baseball to reach its maximum height? Now I actually want to take questions C and D together. C says, how long does it take for the baseball to reach its maximum height? And question D says, what is the maximum height? So it's really asking me two questions about the maximum. Now let's envision the pop fly. It's going to go up, it's going to hit its maximum height, and then it's going to come back down. The maximum height is the vertex of our parabola. Now remember, we calculate the vertex as negative b over 2a, f of negative b over 2a. That vertex has two components. It has an x-coordinate and a y-coordinate. But do note that in our model, instead of using the variable x as the independent variable, we have t. So we know the first component here is going to be the time, t, and the second component is going to be the y value. What comes out of this function is the height of the ball. So when question C says, how long does it take for the baseball to reach its maximum height? I know it's asking me about the vertex, and in particular, it's asking me about the time value of the vertex. So we just need the first component of the ordered pair for our vertex. That means we need to calculate negative b over 2a. So looking at our model, b is 34.3. A is our leading coefficient, negative 4.9. So we will approximate this with the calculator. So in the numerator, we have negative 34.3. And in the denominator, we have 2 times negative 4.9. So this gives us, it comes out exactly 3.5 seconds. So our time to reach the maximum height is 3.5 seconds. The next question says, what is the maximum height? So that's basically asking me, what's the y-coordinate of the vertex? The x-coordinate gives me the time that it takes the ball to reach that vertex. This tells me the actual height of that vertex. So we need the second component of our vertex, our height, which would be f of negative b over 2a. So we're going to take our 3.5 seconds and we're going to plug it back into our function up here. Let me take a look at it. We have negative 4.9 times 3.5 squared plus 34.3 times 3.5 plus 1. Okay, let's type that into our calculator and see how high this pop fly travels. Looks like our maximum height is 61.025, and that is going to be measured in meters. 61.025 meters. Now the next question is also pretty interesting. It says, how much time does the catcher have to intercept the ball before it hits the ground? So how much time, it's asking me about a t value, does the catcher have to intercept the ball before it hits the ground? Now when the ball hits the ground, its height is equal to 0. So what we want to do is set the height equal to 0 and then solve for t. So as a reminder, our function is h of t equals negative 4.9 t squared plus 34.3 t plus 1. So we're going to set the height equal to 0, and then we're going to solve for t. Notice this is a one variable quadratic equation, and I don't think this one is easy to factor, so we'll resort to the quadratic formula. So the t value of our solution is going to be negative b, that's negative 34.3, plus or minus the square root of b squared minus 4 times a, which is negative 4.9, times c, which is 1, all divided by 2 times a. So there's actually two possible answers here, one with the plus and one with the minus. I'll start by entering the one with the minus. So we have alpha y equals, to enter our fraction, negative 34.3 minus square root 34.3 squared minus 4 times negative 4.9 times 1, all divided by 2 times negative 4.9. So one possible answer, if we round to, as the question indicated, the nearest hundredth, one possible answer is 7.0. So t is approximately equal to 7.0, and that's seconds. But we did have another solution, one with a plus in between the two terms in the numerator. So I'm going to do the key combination, second enter, to recall everything that I just typed in, and then I'm going to use my arrow keys to change that minus to a plus. And this one gives us, to the nearest hundredth, negative 0, oh, I'm sorry, hundredth is 2 decimal places, right? How about 7.03 for the first one, and negative 0.03 for the second one, hundredth. So we have two possible answers, but only one is feasible, right? We're just looking at how much time between when the batter hits the pop fly does the catcher have to catch it? Well, that's only going to be a positive amount of time. So we can make our conclusion. The catcher has 7.03 seconds to catch the ball and get the out before it hits the ground. I can just see that catcher popping up out of his place, throwing off his mask, and running to catch that ball to get the out for his team. So next time you go to a baseball game, I hope you also think about quadratic functions.